So our next speaker now is Thomas Hertog. He's going to talk about a quantum cosmology. Where is the title? So his talk is about quantum cosmology.
There we go.
Perspective on fine-tuning.
Okay, well, first of all, thanks for the invitation to speak here, and thank you, Bernard, for an excellent introduction. I think I have rarely had the occasion to speak about quantum cosmology after such an excellent introduction to set the scene. So I'm going to be rather focused in the sense that I'm going to talk about quantum cosmology to illustrate many of the ideas in to do with fine-tuning that Bernard talked about. So many of the things that Bernard mentioned are going to enter my story, leading ultimately to, I think, what the quantum cosmology perspective is on fine-tuning, and then we can discuss its implications. I'm going to do this using two simple examples of fine-tuning. Both were mentioned by Bernard. First one is inflation in the early universe. It's often argued to be unlikely. Right? So that Bernard mentioned that a priori, he even gave an estimate by Carroll that a priori inflation may not be that likely. It leads to a lot of interesting predictions, but what makes it occur in the first place? And the second example is the cosmological constant. And similarly for the amplitude of the primordial fluctuations. My key message will be that apparent fine-tunings can be quantified and interpreted in the framework of quantum cosmology. And by interpreted, I mean you can decide to what extent it's mysterious. And so I'll make that statement. The goal of my talk is to make that statement precise. Now, before I go into quantum cosmology, and especially on this day where we have a Lemaitre celebration later on, I cannot resist drawing your attention to the birth of quantum cosmology in the little article that Bernard referred to, The Beginning of the World from the Point of View of Quantum Theory, published in Nature in 1931, where Lemaitre essentially ends by saying, instead from the same quantum beginning, widely different universes could have evolved. So this is the multiverse avant la lettre, so to speak. Evidently, you don't see any formula in this paper. There were, in a way, the methods or the methodology in cosmology wasn't developed at the time. Really, what quantum cosmology is doing is making this very visionary qualitative statement a little more precise. And the central object in quantum cosmology, from which everything else, I will say, deduces, follows, including predictions for observations, including statements about fine-tuning. Quantum cosmology starts from the abstract notion of a quantum state of the universe. And the key point about a quantum state of the universe is that the quantum state is a function of the geometry and the matter field configuration. This means that quantum cosmology pretty much automatically describes more than one universe. Okay? We have a fixed geometry. Take a time slice of the universe, fix the geometry. That is but one specific argument, so to speak, on which the quantum state is defined. The state is defined on the configuration space, on superspace, on the configuration space of geometries. So it naturally describes a multiverse. Now, for illustrative purposes, and because this is the state I know best, I'm going to work with a specific proposal for the quantum state, because it's only when I specify the quantum state that I can say anything about observables, predictions, and so forth. So I'm going to work with what is perhaps the most famous quantum state, the no-boundary state proposed by Hartley and Hawking in 1983, which is essentially an analog of a ground state construction in field theory. So it involves the Euclidean action and a weighting of different universes specified by the Euclidean action needed to describe the creation of different geometries. The key physical feature of the no-boundary state is this regularity condition on the geometries that contribute. So very loosely speaking, what the no-boundary proposal amounts to, in fact, it amounts to a sort of regularization procedure of the initial singularity in classical cosmology in terms of a regular geometric construction. That is very loosely what is going on. A priori, this is pulled out of thin air. This is just a proposal. And one can explore it, or one can modify it, or one can try to derive it from a more fundamental framework, and so forth. But in any case, this is what it does. You have a classical history, a classical geometry, but the Big Bang is replaced by a regular geometric construction, which emerges, this whole thing emerges as a saddle point of the no-boundary quantum state. So in more geometric pictures, what is happening here in these no-boundary constructions is a kind of Euclidean domain, because otherwise you wouldn't be able to regularize those cosmologies. So the saddle points consist, in fact, of a Euclidean geometry smoothly going over into a real Lorentzian, usual classical cosmological history. Those cosmologies, because of this construction, because of this Euclidean part in the geometries, they come with a certain weighting. The Euclidean action is not zero. In fact, it depends on this. It depends on this construction, and so ultimately it depends on the final configuration, because a different final configuration will require a different saddle point down at the bottom here. So the different classical cosmologies, they come with a certain relative probability given by the quantum states. That's the important point. It's not just a multiverse. It's a multiverse that comes with a probability measure that is given by the quantum state. And the last part is the crucial part. That's where everything, where all the physics lies. Now, the very first thing you ought to do is to, when you start from a wave function, is to see, well, how does really, what kind of classical cosmologies do you really get from this kind of regularity construction? What is classical cosmology, in fact, in quantum cosmology? Well, if you start from a wave function, the naive thing to do would be to look for regions of configuration space where the wave function takes a WKB form. If its phase varies rapidly in configuration space compared to its amplitude, then the wave function has a WKB interpretation and will predict that the configuration G phi here, evolves as a classical universe. So that's essentially the Lorentzian usual Einstein equations emerge from the quantum constraint that the wave function obeys. Each of these universes then comes with a certain probability given by the amplitude of the wave function, and that's what differentiates different cosmologies. So here we have our multiverse. So now let me come to inflation, and let me treat a very simple model. So I'm going to take a dynamical model of Einstein gravity coupled to a scalar field in a quadratic potential. And now we're going to look at inflation from this quantum cosmology perspective. The classical fine-tuning issue is simply that universes with an early period of inflation occupy a small part, an exponentially small part of the configuration space. Essentially, the scalar field must be high up its potential in the beginning. In quantum cosmology, you do not populate this entire phase space. As I said, you only get certain classical cosmologies emerging from a quantum beginning in a given quantum state. The quantum state selects a slice through the phase space of possible universes. So it's a very sharply defined question. Is a period of inflation fine-tuned or not? in quantum cosmology, it's the question, what are the universes that are selected in a given quantum state? Graphically, the no-boundary wave function will predict a slice through all possible universes. Does that slice coincide or not, or cross the inflation, the narrow band of inflating universes? What I regard as the biggest success of the no-boundary quantum state is that apparently the no-boundary quantum state predicts exactly those inflating universes. It predicts inflation. In other words, it is from this regularized quantum origin, only universes emerge which have, only classical universes emerge which have an initial period of inflation. Maybe I should not, yeah, so the construction requires more, the explanation requires more details about the saddle points, but the key point is intuitive, really. It's only when you have classically, when you have an early period of inflation, in which, in other words, the dynamics is governed or dominated by the scalar potential and not by gradient or kinetic energy, it's only under those circumstances that you can regularize, that you can round this off geometrically in a regularized fashion. So this is an example of, in that quadratic potential, of a bunch of classical universes that are predicted by the no-boundary wave function. The different curves on this graph represent different classical universes, which are in the ensemble, in the multiverse predicted by the boundary state. And you see here the Hubble rate versus phi, and that characteristic line, they line up when you evolve them towards the past, they all line up around a characteristic line which is specific to inflating universes. Then they have different amounts of inflation. Here you see that they vary a lot. These are those universes at very early times. They have different amounts of inflation, and this guy has more inflation than this guy, for instance. Yeah? But in any case, we seem to be nicely lined up. Nicely, the quantum state nicely focuses us on that particular part of phase space where corresponding to inflating universes. Now, these different examples of those inflating universes that I show there have a relative weighting determined by the value of the Euclidean action of the no-boundary saddle point. That gives us relative probabilities for different amounts of inflation. And this is a sketch of those probabilities. You have to take e to the minus to the real part of the Euclidean action, and you see that the probability given by the no-boundary state is very much favoring universes with a small amount of inflation. Phi naught here is sort of the initial value of the scalar field. The larger the initial value, the higher the action, the smaller the probability. So universes with a low amount of inflation seem to be heavily favored in the no-boundary state. So you might still ask a question, well, maybe inflation is fine-tuned also in quantum cosmology, because we happen to observe a universe, we happen to find ourselves in a universe with a long period of inflation, which has a very small prior probability. But in order to make the link between the probabilities given by the quantum state and probabilities for our observations, there's one more step that we need to take. We have to take into account our observational situation. And now comes the entropic part, so to speak, of quantum cosmology. And this is how it enters. How do you do entropic reasoning in quantum cosmology? You calculate conditional probabilities. So in principle, all sorts of probabilities are derivable from the wave function. Probabilities for different amounts of inflation, probabilities for sorts of fluctuations. Also conditional probabilities can be calculated in quantum cosmology. predictions for observations are conditional probabilities for unobservable, like one or another CMB feature, given the existence of our observational situation, and now comes the key point, as a physical system within the universe. The way entropic reasoning emerges or is done in quantum cosmology is not by invoking an additional principle, a weak or a strong entropic principle. No, it's simply done by considering those probabilities given by the quantum state which have anything to do with our observations. And by R, in quantum cosmology, we mean an observation situation characterized by some data D, which are a physical system within the universe. So it could be anything. It's not entropically focused. It could be some measure of complexity or the fact that we have a local distribution of galaxies or whatever. So really what we have advocated in a number of papers, is that we test the multiverse predictions in quantum cosmology by a specific set of correlations. You could view this as a correlation between, on the one hand, our existence, our observational situation, and on the other hand, some feature, some observable of the universe. This is what we have. This is the situation. We are part of the universe. This is the way that fact is incorporated in quantum cosmology. So if you want to say whether inflation is likely or not, or how to test the multiverse, or how to derive predictions for our observations in the multiverse, this is the way you could do it in quantum cosmology. So let me now go back to the issue of inflation. This is a rather messy formula, perhaps, but it's at the core of it is very simple. Let me very, very qualitatively evaluate this conditional probability and take for as an observable the number of E-folds, what we were discussing, the number of E-folds of inflation. Is it big or is it not big? There are two elements to this, right? You could write this out in terms of you sum over all the histories, all the universes you have in the multiverse. Each universe comes with a different weighting. That's the no boundary weighting of different universes, which I discussed. But it's now multiplied by the probability that our observational situation exists in those different universes. And you could see where this is going, right? If I have a low amount of inflation, just a few E-folds, then I will produce a universe which is, one, empty, and secondly, not lived very long. It's going to recollapse because all these universes are fundamentally closed in the no-boundary state. So, in those universes, this probability is going to be very small. The probability that our observational situation described by a local distribution of galaxies exists in a universe which has only a few E-folds of inflation is very small. They don't exist even long enough. On the other hand, the probability for a large number of E-folds is very much suppressed by the no-boundary quantum state weighting. And so it's going to be an interplay between these two elements as to what has the highest probability. So here is a very rough characterization of taking into account the observational situation. And roughly speaking, so if you have to compare with this graph, roughly speaking, the condition on the existence of our observational situation has a big impact on the probability distribution and, in fact, favors the large universes produced by many E-folds of inflation. And that has an implication of your analysis, your understanding, your interpretation of whether or not inflation is fine-tuned. So this is, regarding inflation, my summary. It requires fine-tuned initial conditions in classical cosmology. It emerges as a prediction in quantum cosmology, but the probability, the prior probability, is low for a long period of inflation, at least in the no-boundary quantum state. Nevertheless, the theory predicts that we should find ourselves in a universe with a long period of inflation, That's saying in word, the conditional probability for a long period of inflation is high because we are part of the system and there are more places for us to be in those larger universes. Put differently, what is most probable to occur is not necessarily what is most probable to be observed. These three steps illustrate how dramatically different your analysis and interpretation is of a fine-tuning issue when you run through the scientific framework provided by quantum cosmology. 5 more minutes? Yeah, okay. I will be brief about the second example. It's sort of a more elaborate example, but exactly the same principles enter. You first determine the probabilities from a quantum state, you convert these, or you derive from these probabilities for our observations, and you draw your conclusions. So evidently, in my simple inflationary model of just a quadratic potential, I can't do all that much. I can't say anything about a cosmological constant or varying the fluctuation amplitude. I have to enlarge my multiverse. I have to enlarge my dynamical model in order to accommodate variations of those features like lambda and q. So I won't do it in a precise manner, but let me just sketch how the argument would work. Consider a more complicated microscopic theory. Consider a landscape model, a landscape potential, which has an ensemble of minima at different values. Those different minima are the different possible values of the cosmological constant in this model. And each of these minima is surrounded by various inflationary patches of the potential. You could, quadratic patches, quartic patches, plateau potentials, consider a large inflationary landscape provided by whatever fundamental theory. How will we work with this? Well, again, the no-boundary wave function in this landscape will select inflationary universes. And it will assign relative probabilities to different inflationary universes, just as before. The wave function itself will predict, just as before, a low amount of inflation. And in fact, a relatively flat distribution over different values of the cosmological constant. The last step is we have to include, when we want to relate to our observations, we have to include a requirement that our observation situation, characterized, for instance, by a local distribution of galaxies, exists. Well, that requirement, as you know very well, this goes back to Weinberg and others, selects a small region in the possible parameter space of values of lambda and q. So far, so good. So now we touch already in the last point, we touch on the Weinberg argument and others. But within that region, selected by the entropic requirement, you say, what operates within that small region? Within that small region, it is not just a flat prior, as Weinberg adopted, as Weinberg assumed. It's again the no-boundary prior within that region that operates. And in fact, that has a large implication. And this is illustrated in this diagram. This diagram is essentially what you know from Weinberg and others, Tegmark, Livio, Ries, and others. The white region is the entropically allowed domain. It's what essentially is selected by requiring our existence one way or another. But what are our predictions within that white region? Weinberg famously derived that the cosmological constant, in fact, comes out just right, until Tegmark came along and said, wait a minute, if you vary Q as well, your cosmological constant shifts and is, in fact, 3 orders of magnitude to larger than what is observed. Tegmark and Weinberg assumed there is no distinction between these different universes in the white region. The prior was flat. We don't have a flat prior. We are just calculating conditional probabilities in the no-boundary quantum state. The no-boundary quantum state turns to favor low Q. But wait a minute, if you favor low Q, you're back to the successful prediction of Weinberg. So even in this intricate example, where a lot of other ingredients enter, there's this impact on the prior, on the final predictions. And evidently, you could enlarge this example to many other features that Bernard talked about. Although you would have to do this in rather specific microscopic models of the multiverse to say anything meaningful. So it's not that we are so keen on our prediction here. I just want to illustrate how quantum cosmology and its wave function go together with the multiverse predicted by microscopic theories, and how the two together lead you to specific predictions. Okay, so now I will conclude with some remarks on a take-home message, take-away message of all this. Quantum cosmology predicts a multiverse that comes with a measure given by the quantum state. I stress that. From this, predictions for our observations can be derived. I illustrated that. And as such, quantum cosmology is a framework in which fine-tunings can be quantified and interpreted. But now what? Some apparent fine-tunings disappear because they're incorporated in this bigger scientific framework in which they appear natural, or in which they're even, by which I mean, in which they're predicted with high conditional probabilities. The example was inflation, a long period of inflation. We are likely to find ourselves in a universe with a long period of inflation in quantum cosmology. That's a very definite, clear, clean statement. But, and now comes the but, and that's, I guess, what interests you most. Some features, other features of our observed universe will not be predicted with high conditional probabilities. I am not claiming that I will be able to play this game for all sorts of parameters and get them right, get them out with high probabilities. In fact, the condition on our observational situation is a way to sort of shrink the parameter space to those correlations that you hope to identify successfully with your theory. If I left out this condition, already my predictions would be all over the place. So the entropic condition here is already a sign of restriction as to what you aim to predict. So it's definitely not going to be the case, at least in the models that we know now, that even if you embed them in a quantum cosmology framework, you're going to get out all these parameters. That's not going to work. What to think about this? Is the theory wrong? Well, my position is very similar to Bernard's on this. I would regard a theory as more successful if it predicts more correlations. If it did more correlations in the form of these conditional probabilities that I talked about. But should we require, or should we hope, or should we believe that we're going to find a theory that predicts all such correlations? It seems to me that that expectation goes against what we know about quantum theory. Quantum theory is probabilistic, so there are bound to be certain accidents, certain quantum accidents of evolution. Should we call these fine-tuned? Maybe not even. Quantum accidents occur. And to take those into account, they will have to go in the conditional part of the probabilities, I believe. So I'll stop there. Thank you.
Yeah, we have time for a few questions. Short questions.
Well, I can't help asking this obvious question, which is that at some point, you know, the scales we observe nowadays left the horizon at the end of inflation. So it doesn't really matter if you have a lot of inflation or not. Basically, what would be nice to have is from your distribution, a prediction for the distribution of the spectral index, the amount of gravity waves, all that stuff.
Yeah,
But unfortunately, it doesn't look like it's possible just from the actual.
no, it's very much possible.
Okay.
It's done.
Tell
yeah,
me about
sure.
it then. Tell me about it.
Sure. It's obvious, right? If you select universes with a large amount of inflation, these are the backgrounds that you select.
It doesn't matter for the NS.
Then all the rest comes along. The wave function of the fluctuations is the usual wave function of
No,
the
you have the
fluctuations.
usual uncertainties, which is
Sorry?
you really could have anything red, any red spectrum, doesn't matter if it's 0.96, 0.91, 0.99. You have the same problem. The R could be 0, could be 0.2, could be 0.1, could be 0.05.
No. The fluctuations are predicted. I didn't talk about the fluctuations because these are the standard predictions around each background of the spectral index and all that.
Yeah, but inflation has a remarkable inability to predict them exactly. And the reason is that
Because
you can have
if-
all kinds of, you have reheating, and as a result, you can have any number of e-foldings you want. Any case, it has to be near the end of inflation that you produce these fluctuations.
Well, the
So if you
details
go
of-
and tell
the
me, well,
details
I
of-
don't have infinite amount of inflation, I have a finite amount of inflation.
Yeah, sure.
Are can you actually push things to the point where you say, oh, this is the reheating temperature, oh, this is the number of e-foldings, this is the NS,
But
exactly.
typically, we don't calculate the reheating temperature to calculate the spectral index of fluctuations or the scalar to tensor, right?
So what is NS?
Tell me your model first.
Well, that's the problem. So
No,
basically,
that's not the
yeah.
problem. Tell me your model. In
Okay.
the m²/phi² model, the NS is the prediction, the standard prediction of the quadratic potential.
So take the space of all the models,
Specify me your model.
take the space of all the inflationary models.
Then the
Because you don't
prediction
know-
of the boundary wave function will be that the spectral index and the features of the fluctuations are those that associated with that model which has the lowest exit of scalar field-driven eternal inflation.
Right. So you say the lowest number of e-foldings.
The lowest exit of the phase of eternal inflation. So I will make this very specific because this is an
interesting.
important point.
So you're saying, basically, you have these consistency conditions, you have these lines, and you're saying you have to be near the end of the line.
No.
So
Be
can we
specific.
just postpone this for the discussion?
No. This is easy. This is easy to resolve. Take a quadratic side and take a plateau side. Okay? So you have two distinct spectral features. If you roll down from that side, or if you roll down from that side, you will observe a different spectral index. My prediction, each of these sides has a regime of eternal inflation high up the hill, high up the quadratic side or near the plateau. My prediction is that we roll down from the side with the where the regime of eternal inflation lies at the lowest value of the potential. So we roll down from the plateau side, and the spectral index on observable scales is that associated with universes rolling down from that side. Okay, you have to give me the parameters of that plateau, right?
Okay, let's continue this in the discussion. We have time for a short question. Is your question short? Very quick? Okay.
So I was wondering about the potential dependence of, in your example, you showed a very simple example with m²/phi² inflationary potential. And you didn't show how your results were in any way model dependent. So for instance, how this distribution that you showed, the probability distribution for the number of e-folds depended on that potential. So if I have a different potential, will that distribution look different?
This is
If I have many
the
fields,
related question.
for instance, will it
Yeah.
look different? Can you say something about that?
Yeah. So, for instance, we worked higher potential values lower the probabilities in the boundary wave function. I think your question is really the same as the other question. We worked this out in great detail, as you know, in deep brain inflation, where your landscape has a specific set of scalar potentials, and we arrived at a prediction that NS in deep brain inflation is 0.948. Whereas without a quantum state, you have NS lies between 0.93 and 1.04. If you give me a specific landscape consisting of a specific ensemble of inflationary patches, my predictions are very sharp. If you give me a different landscape, my predictions will evidently be different. If you give me a landscape that doesn't allow blue spectra, evidently I'm not going to find blue spectra. And this 0.94 is the limit in deep brain inflation, where you have a large number of E-folds. All universes in deep brain inflation with a large number of E-folds have this very characteristic NS. The no-boundary wave function selects those universes with a large number of E-folds.
Okay, so I think
No,
we
no,
should move on to the next speaker. So let's thank Thomas again.